Hi everyone. So these are the 4.1 notes about maxes and mins, maximums and minimums of a function. So the first thing I want to talk about are some, the terms. Absolute, maximum, or minimum versus local, maximum, or minimum. So if you have a function, sorry, that's very crooked, but that's okay. Let's say it looks like this. Something like that. Whatever. And, it's on this interval A to B. It's a closed interval. A closed interval means that the endpoints are included, bracket, in the interval. So if these were open circles, that would be an open interval. So we're talking about closed intervals. So what you can have basically are local maxes and minimums and absolute maxes and minimums, or you don't have to have everything. For example, in this problem, that point would be an absolute minimum because there is literally nothing lower than this point in the graph. Is it a local minimum? No, because local maxes and maximums and minimums cannot be endpoints of the interval. So if you go to this point right here, first of all, is it an absolute maximum? Because it goes up, so it can't be a minimum. Is it the absolute highest point in this graph? No, because that one's higher. So it's not an absolute maximum. Well, is it a local maximum? No, because an endpoint cannot be a local anything. It cannot be a local, it cannot be a local maximum. It can't be a local minimum. So, don't forget. Gosh, I can't spell today. Endpoints of an interval cannot be local. And I'm writing local. Local means local max or local min. Okay, so then we've got this point here. That's certainly not the absolute most highest point, but it does go up and then down. So if you notice points lower on either side of that dot, then we have a local maximum. Okay, here we've got points on either side of this dot that are higher than it. So this would be a local minimum. Okay, here, that dot right there, that would be, it is the absolute highest point in this graph, so it is the absolute maximum, but because it's not an endpoint, it is also a local maximum. So it has two terms, this one. So all maxes and mins can be local as long as they're not endpoints. And then we've got this one. Well, it's certainly not the absolute lowest that this graph goes because the absolute minimum was here, but it is a minimum because the points around it are higher than it. So on either side of the dot. So this would be a local minimum. Let me draw another one for you. What about a graph like this? Open circle, closed dot. Okay, so this is on a closed interval A to B, right? Because both endpoints are filled. Endpoints of the interval. These are not endpoints. So let's categorize all of these. So what would this be? It is, so the points on this side of this dot are higher than it. So you would think it would be a minimum. First of all, it's not the absolute lowest point in this graph, so it's not an absolute minimum. And it's an endpoint, so it can't be a local anything. So guess what? This point doesn't have a name. It's really nothing. It's not called anything. Not that it's nothing, it is a point, but it doesn't have a name. So no name. That is not a point, so also no name. Okay. How about this one? Well, is it a local maximum? Is it an absolute maximum? Are all points around this point on the left of it and the right of it higher than it? No, because the points on this side right here are higher than it. And then on this side, on the right side of the dot, they're lower than it. So it's also a nothing. It doesn't have a name. Then there's this point to discuss. So it's an endpoint, meaning it can't be local anything, but is it an absolute something? Well, it's the lowest point the graph goes, so it is an absolute minimum. Okay, so then we have what we call Fermat's theorem. That's Fermat, okay, Fermat's theorem. And Fermat's theorem is the sentence. It says if the function f, so f is, f of x, has a local maximum or minimum at x equals c, some value on the x-axis, and if f prime of c exists, that means it's differentiable, the function, you can differentiate it, then what's going to happen is that the derivative is going to equal 0, which, you know what, you guys, you already knew this. You know that when you find the derivative and set it equal to 0, you're looking for a maximum or a minimum, because remember, at a maximum or a minimum, what's the slope of the tangent line, also known as f prime? It's 0, right? So we already knew this. Fermat's theorem is saying that. It's saying if you have a function, you don't have like a corner or a cusp, and it's differentiable. F prime of c means differentiable. Okay. If you see you have a smooth curve and you can find the derivative and you're finding it at a maximum or a minimum, then you know the derivative is going to equal 0. Okay. Number 3. We're actually halfway down through the notes. This is going to be short, so pay attention. The definition of a critical number. What is a critical number? Okay. This is a definition. A critical number, so hold on. A function f has a number c in the domain of f such that f prime of c equals 0 or f prime of c doesn't exist. Okay, so in human words, a critical number is where the derivative equals 0 or is undefined. That's what it means. So if I give you a function and I say, okay, find all the critical numbers, your task is to find the derivative and then find all the x values where your derivative would equal 0 and all the x values that would make the function undefined. For example, let me quickly do one. Pretend you have found the derivative, okay? There's some function, whatever. Let's say you found the derivative and this is what you discovered. So that's the derivative function. Then the critical numbers of f of x, okay, are going to be where its derivative is equal to 0. So that's where the numerator is going to equal 0 when x is -3. And where the derivative is undefined, well, that would come from the denominator 4. Okay, so -3 would make the derivative equal 0. Imagine plugging in a -3. That would be 0 over whatever. And then imagine plugging in a 4, you get something over 0. that would make the derivative undefined. So the combination of those two things, where the derivative is equal to 0 and where the derivative is undefined, are called the critical numbers. Okay, so that's really important for you to remember. All right, and then we've got one last thing left on the notes, and it's called the closed interval method. Okay, and it's used to find absolute maximums and minimums in a closed interval. So I'm going to start this because it's probably the most important part of the notes. So there's a process actually. So it says to find the absolute maximum and minimum values of a, super important word, continuous function f, okay, on a closed interval, and I told you that's an interval where it's bracketed, okay, a to b. Follow the following 3 steps. So step 1, find the values of f at the critical numbers in A to B. Okay? Step 2, find the values of f at the endpoints A and B. And step 3, the largest of the values from steps 1 and 2 will be the absolute max and the smallest of the values from steps 1 and 2 will be the absolute min. I want to do 2 examples with you and I'm going to end the notes. So example 1 for the closed interval method. For example, suppose I give you some polynomial x cubed minus 3x squared plus 1, and I'm only talking about the interval from -1/2 to 4, and the directions are find the absolute max, find the absolute min. So first things first, find all the critical numbers. That means find the derivative, which is 3x squared minus 6x, okay? So you have to find the critical numbers so you can plug them into f of x, all right? So here's the derivative. You want to set it equal to 0 because your critical numbers are where the derivative equals 0 and where the derivative is undefined. I'm thinking since our derivative is yet another polynomial, we will not have any undefined values, which is fine. So I'm going to factor out a 3x, leaving me with x minus 2. So it looks like I've got x equals 0 and x equals 2 as my only critical numbers. Step 2 says, I'm still in step 1, find the values of f at the critical numbers. So I'm going to set up a table of values. It says find the values of x, meaning find the points. So I have to put a 0 in here and a 2. So when I plug in a 0 into f, not f prime, notice, into f, I plug it in, I get a 1. And when I plug in a 2, I get a -3. I did the work ahead of time for you, so I don't waste your time on the notes. And we're plugging it into f. Step 2 says find the values of f at the endpoints. So I have to include the -1/2 and the 4 in my chart. So when I plug in a -1/2 into f, I get 1/8. And when I plug in a 4 into f, I get 17. Step 3 says look at your table of values and decide what's the max, what's the min. So it looks like I've got the absolute maximum here at 4, 17. It's a point on the actual graph. And I've got my absolute minimum right here at -3 because that's the smallest y value in the chart, right? That's it. That's how you do it. So you say, 2, -3 is the absolute min, and 4, 17 is the absolute max. I want to do one more example so you really understand it, and then that's it. So example 2, for the closed interval method, what if f of x is equal to x minus 2 sine x? So the closed interval method says find the critical numbers. So let's do that first, meaning find the derivative. The derivative of x minus 2 sine x is 1 minus 2 cosine x. Set it equal to 0 and find all the zeros and all the places where this function is undefined. So if I do that, I get cosine x equals 1/2. I don't think cosine is ever undefined, so I'm actually not going to get any values that make my function undefined. But I do have, oh, I forgot to tell you the interval, 0 to 2 pi, sorry. So I have to get all the x values between 0 and 2 pi where cosine is equal to 1/2. Those would be pi over 3 and 5 pi over 3. The closed interval method, those 3 steps, say, think of the values of f of x, not f prime, at the critical numbers. So pi over 3, 5 pi over 3. Step 2 of the method says also evaluate at the endpoints, right? At the 0 and the 2 pi, the a and the b. So when you plug it in, I already did this, into f, this is f. When you plug in a 0, you get 0. When you plug in pi over 3, you actually get pi over 3 minus rad 3. And then when you plug in 5 pi over 3 into the original f, you get 5 pi over 3 plus rad 3. And then when you plug in 2 pi into the original, you get 2 pi. So 0 is just 0. When you plug in pi over 3 minus rad 3 into the calculator, it's the decimal negative 0.685. I'm rounding. This one, 5 pi over 3 plus rad 3, gives you 6.968. And then 2 pi is approximately 6.28. So you have 4 values to compare. Which one is the absolute maximum? Clearly 6.968. So here's our absolute maximum. And which one's our absolute minimum? It's the negative. It's the smallest one. So absolute minimum. And that's how you find them, okay? You have to have a value, kind of a t-chart, an xy chart, where you plug in the critical values. Those were the critical numbers. This is the A and this is the B. That is what your chart has to be comprised of, those values. And sometimes there might be more critical numbers, sometimes there might be less. And then you do a comparison of all the y values to see which one's the highest and which one's the lowest. And that's the end of the notes.